Welcome to Engineering, Mathematics and Modeling Week 1, where we'll be discussing vectors. We'll be discussing some properties of vectors and some operations on vectors. But first, what is a vector? Well, in physics, we have many properties like mass. We have things like a force, velocity, and temperature. And a vector is something in physics that we can classify as having a magnitude and a direction. Now, take for example mass. Mass has a magnitude, but it doesn't have a direction. Force has a magnitude. We have a force of 3 newtons working on an object from above. Velocity, we can have an object traveling at 3 meters per second in a certain direction, but temperature doesn't have a direction, it only has a magnitude. So if it has a magnitude but not a direction, it is not a vector, but it is a scalar. And if it has a magnitude and a direction, we call it a vector. So mass and temperature were scalars, and force and velocity were vectors. Now, to ensure that everybody knows what we're talking about when we write something down, let's look at the second law of Newton. We have a force, an acceleration, and a mass. Now we know the force is a vector, the acceleration is also a vector, and the mass is a scalar. To differentiate between these in notation, we can write an arrow or a dash above the letter or the concept that we're using. Now, mathematically, a vector is just a point in a space that has certain properties. A space that we're all very familiar with is the two-dimensional space, where we have an x and a y and an origin. We can write out points in this space. For example, the point 3, 4 is this point 3, 4, it has x coordinate 3 and y coordinate 4. This space is known as R2, the two-dimensional space where we look at real numbers, and we'll talk more about different types of numbers later in this course. We also have a three-dimensional space, which we're also familiar with, which we will denote with R3. Now, points in these spaces have an x and a y coordinate, well, for R2, and we can denote some vector a in this space as ax and ay, and sometimes we leave out the x and the y, we call them 1 and 2, but the idea is clear. We have a column with multiple entries. In a three-dimensional space, we would have ax, ay, and az, denoting the x, y, and z coordinates. Vectors in a space like this, we usually denote not just with a point, but we have an arrow pointing to the point in the space we're looking at. I will not attempt to write, 3D is harder to draw, but the idea is similar. We have an arrow in our space. So when we look at vectors now, we know that it has a magnitude and a direction. We know how to write it down. Some people will also write a row instead of a column. Doesn't really matter. Traditionally we write columns, and we know how to visualize it. But we said that a vector has a magnitude and a direction. If we look at this arrow here, it is clear that it has a certain length. And the length of a vector, if I call this vector A, the length of a vector is denoted by the name of the vector with 2 vertical bars. And this is called the modulus of vector A. I'll just use a new pen. Now we also know that it has a direction, but direction, we first need to define how we view direction. Well, direction is the angle, and I'll denote it with theta. Theta is the direction, or the direction or the argument of the vector, and we start at the positive x-axis. So 0 will be here, 90 degrees will be here, 180 degrees, 270 degrees, and 360 degrees. Now we can also do that in radians, where we start at 0, pi over 2, pi, 3 pi over 2, and 2 pi. But we measure this angle from the positive x-axis. And this is the case in 2D space. Now let's have a look at this vector, and let's have a look at this triangle. We know that if this is the length of A, and we know the length of this part of the triangle, because that is its x-coordinate, and this is its y-coordinate. And we also know that this is a 90-degree angle. We can use Pythagoras' theorem to determine what this length is. The length of a vector is the square root of its x-coordinate squared plus its y-coordinate squared. And its angle theta is there. So we will be using this triangle a lot more. Now, if we have a vector in 2D, it's clear. But for a vector in 3D, if we have this vector here, what is the length of our vector AX, AY, and AZ? Well, it's basically the Pythagorean theorem, but then in 3 dimensions. It's the square root of AX squared plus AY squared plus AZ squared. And we can do this for vectors of any length, any number of dimensions. So if we have a vector of length 1000, we can do this as well. And of course, we're used to 2D space and 3D space, but if you're using vectors to store information, they can become a lot longer. So we have looked at what a vector is. We have seen that it is a point mathematically in a certain space, like R2 or R3. We see that it has a length and direction, and we've defined what the length of a vector is and what the direction of a vector is. Now, that direction for 2 dimensions, that's clear because we can visualize it very easily. If we look at 3 dimensions, it's not so easy. So I will just remove this and make an attempt to draw this in 3 dimensions. And what you'll see is that if we have our vector somewhere in space, this is A, which is AX, AY, AZ. And if we want to determine the direction, but then with respect to what? Because we have an angle here, if this is X, Y, and Z, we have an angle here, let's call it theta Y. We have an angle with respect to the x-axis, theta X, and we have one with respect to the z-axis. So a vector in 3D is not defined by one angle, it is defined by 3. And let's write down the definitions of those angles, or the relationship of those angles. And we have that if we take theta x, this is equal, well, not theta x itself, but the cosine of theta x is equal to ax over the length of A. The cosine of theta y is ay over the length of A, and the cosine of theta z is equal to az over the length of Z. And defining angles in 2 dimensions is easy. In 3 it becomes cumbersome. In multiple dimensions you would use something like this, but then typically we don't use that anymore. So we have vectors, the definition, some properties like length and direction, and we do that in 2D, and we will also do it in 3D, but we won't be calculating anything for higher dimensions by hand. In the next video, we'll talk about operations such like addition and multiplication on vectors.